Road to Olympiad.
Welcome to RTO. Consider the following problem. Let f be a function from positive integer to positive integer satisfying a for every positive integer n, f of n plus f of n is equal to f of n. B for some positive integer n naught, f of n naught is equal to 1. Show that f of n is equal to 1 for all positive integer n. Given the image of certain object is 1, we want to show that all images are 1. This may seem doable by using induction, but is only for those integer greater than or equal to n0. What about those less than n0? Later we'll show one common way to prove it. Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve this problem, we start by doing the induction work. Since f of n0 is equal to 1 for some positive integer n0, it's follow that f of n0 plus 1 is equal to f of n0 plus f of n0, since 1 is equal to f of n0. And this is equal to f of n0 by the condition A given by the problems. And by condition B, this is also equal to 1. Therefore, by inductions, f of n is equal to 1 for all positive integer n greater than n0. For the case where n is less than n0, we consider the set S consisting of all the positive integer n such that f of n is not equal to 1. Since we have proven that f of n is equal to 1 for all positive integer n greater than or equal to n0, all the element in S, if there's any, must be all less than n0. This is to say that S is a finite set. And since S is a finite set, and if it is not empty, there must be a greatest element in it, say capital N. Then by condition A again, we have f of capital N plus f of capital N is equal to f of capital N. And this is not equal to 1 by our assumption. However, this means that f of capital N plus f of capital N is not equal to 1. Or in other words, capital N plus f of capital N is also an element in S, because f of capital N is also a positive integers. This is impossible since capital N plus f of capital N is clearly greater than n. But n, by the assumption, is already the greatest element in S. Therefore, we reach a contradiction and thus S must be an empty set. In other words, there is no positive integer n such that f of n is not equal to 1, or f of n is equal to 1 for all positive integer n. And this marks the end of our proof. Post in the comment below if you have any thought on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.